Let's begin by making a few comments about the nature of a linear transformation. Suppose I have two vector spaces, two abstract vector spaces, which I'll call V and W. These need not be the same vector space, though they could be. And by vector, I mean in the abstract sense of an abstract vector, not necessarily a geometric directed magnitude, as we have been talking about, but an abstract vector. And I consider some generic transformation, let me call that F, that takes elements within V and maps them to elements in W. Just some generic mapping from V into W. Now, if you imagine collecting those all together, considering the collection of all possible transformations of V into W, let me symbolize that by T for transformation. Now, what we're interested in this video is a special subset of those transformations, the linear transformations, which I'll designate by LT, that special subset of the set of all possible transformations. But now the question is, what makes something a linear transformation specifically, as opposed to a nonlinear transformation, which you can imagine being over here? What makes something a linear transformation specifically? What's that special extra feature that you have to add to just a generic transformation to make it a linear transformation specifically? There are actually two requirements that we demand of F to say that it's a linear transformation specifically, although we're going to see that those two can actually be boiled down to one after that. The first is that if we consider F acting upon a sum of two vectors, let's say x plus y, x and y are drawn from this first vector space, we demand that this be equal to f of x plus f of y. That's the first stipulation to say that it's a linear transformation. The second is that f acting upon a scalar multiple of x, let's say lambda of x, is equal to that very same scalar multiple times f of x. These are the two requirements to say that f is a linear transformation. So if f has these two features, that f of x plus y is equal to f of x plus f of y, and that f of lambda x is equal to lambda of f of x, then we say that f is a linear transformation. Now let's think a little bit more about these two requirements. What are they saying? Let's consider this one first. We have two vectors, x and y, drawn from this input vector space. What this is saying is that if f is a linear transformation, we can either add the two, x and y, in this first vector space, and then operate through f to get our target vector in W. Or what we could do is we could take those x and y, which are again drawn from V. We can map those to something in W. So this thing is going to be in W, f of x is going to be in W, f of y is going to be in that vector space W, and then you can add those two in the target vector space. So if f is a linear transformation, those two processes are the very same thing. They generate the very same vector in W. Correspondingly, if we think about what this second line is saying here, if we have some vector x, which is again drawn from V, if we scale in the vector space V and then operate upon it with f, if f is a linear transformation, that's the very same thing as just taking that first vector drawn from V, x, mapping it through f into the target space W, and then in the target space, scaling by that very same factor lambda. If f is a linear transformation, those two processes are the very same thing. So let's think about what these two lines are saying of f in a little bit more detail. So let's say I have two blobs here. The first blob is going to represent the input vector space V, and the second is going to represent the target vector space W. And let's just read what this first line is saying, what's going on with x and y and the outputs. What does the left-hand side say? It says we have two things in the input vector space V called x and y. Let's say that represents x, that represents y. We consider the sum in the vector space V first. So let's sum those two together. They're joined together and they're summed into something else in V, which is called x plus y. And then we operate upon this with the map f to send it into something in the target vector space W. So this is going to be f acting on x plus y. And this line from this blob to this blob represents the action of f. So that's where we end up with the left-hand side here. What is the right-hand side saying? It's saying we have x and y, which are in that input vector space V. We consider f acting on both of those first. So we start at x here. We map it using f into something in the target vector space W. So that's going to be f of x. And let's say we have y here. We're going to map that to something in W. That's going to be f of y. And then we sum those two, f of x and f of y, in the target vector space W. So we're going to, again, join those two. Now, if f is a linear transformation, this goes to that very same thing, f of x plus y. That's going to be equal to f of x plus f of y. So if f is linear, it's saying that those two processes that we just drew out here are going to land at the same destination here. In a similar way, let's think about what the second line is saying. So let's read the left-hand side first. So we have f of lambda times x. So we have x first, which is already drawn here in the input vector space V. Scale it by this factor lambda. So let's draw that in. The scaling is going to be done in this vector space V, the input vector space. So that's going to get scaled to something, which is called lambda times x. And then we operate upon lambda x with f. That's going to send it to something in W. That thing is going to be called f of lambda x. And that mapping is how f works. That's what the left-hand side is saying. So we go from here, there, to there. The right-hand side is saying, let's first consider x, which I have over here. Operate upon x with f, which I've already got drawn down here. That's from there, from here to there, down there, f of x. And then scale it by lambda in the target vector space W. Now, if f is a linear map, that scaling is going to go from here to that very same thing over there. That's going to be equal to lambda times f of x. There to there is lambda times f of x. So if f is a linear map, then those operations relate in that way that we've just drawn down there. So I think when you draw all this out, what is being said by these two lines here, as we have done, it shows why we care about linear transformations between vector spaces in the abstract sense, and that it preserves the structure of two operations that we commonly do with vectors, namely vector addition in this first line and scalar multiplication in the second line. And it preserves the structure of these two operations between these two vector spaces, V and W. In that vector addition plays nicely with f. It relates nicely with f in such ways that you can do vector addition over here with the respective inputs in V, or you can do vector addition with its respective inputs in W. And f works in such a way with vector addition as you get to the same destination vector in W over here, which was f of x plus y. And you can say a similar sort of thing with scalar multiplication. That scalar multiplication relates nicely with f in such a way as you can do scalar multiplication with its input, which was x over here, and it was that line over there. And scalar multiplication with its respective input, which over here was f of x, and you get to the very same destination down here in W, that f relates nicely to scalar multiplication in this way. Now, I claimed before that this line and this line can be unified into one statement about what makes a transformation a linear transformation specifically, as opposed to a nonlinear transformation. And let's find out what that respective statement is going to be. To find out what that is, let's consider not f of just x plus y or lambda times x, but let's say alpha times x, where alpha is a constant, and beta y, where alpha and beta are constants, x and y are the vectors in V. Now let's examine this thing. Now the first line says that if I have two vectors, I can break them apart like this. My two vectors here are alpha x and beta y, so that first line allows me to say that this is equal to f acting on alpha x plus f acting upon beta y. Now, this second line here says that scalars can be moved to the front. That's going to do with both those terms. So this is equal to alpha times f of x plus beta times f of y. So we see that if we have f of alpha x plus beta y, where alpha and beta are the scalars, x and y are the vectors, then this is equal to, if f is a linear transformation, that these two lines are true, alpha times f of x plus beta times f of y. And that the truth of 1 and 2 imply the truth of this statement. And we can prove the converse very easily, that the truth of this statement implies the truth of both 1 and 2. To show that implies the truth of 1, simply set alpha and beta both equal to 1. To show that implies the truth of that second statement, leave alpha alone as that undetermined scalar. Instead of calling it lambda, call it alpha. And then set beta equal to 0. So, a transformation is linear if and only if this is true of that transformation f. Let's consider a few examples of linear transformations. One important class of linear transformations would be the rotations. Let's consider the specific rotation in which we rotate by pi over 2 radians counterclockwise. Let me call such a linear transformation r for rotation. Let's say we're working in 2 dimensions, and let's consider this vector, which I'll call u, and this vector, which I'll call v. Let's operate on u and v with the map r. U gets mapped to that vector, which is going to be r of u. V gets mapped to this vector, which is r of v. These are at right angles, and these are at right angles, because that's how we set up the transformation. Now let's consider the vector sum r of u plus r of v. So we consider the vector sum. That's going to be that vector approximately, r of u plus r of v. Now, if this transformation is linear, which it is, that should be equal to the rotation acting upon u plus v. Let's add u and v here. Let's have that go that way. Then have the vector sum here. So that vector there is u plus w. And then we take u plus v and then rotate it pi over 2 radians counterclockwise to that vector. And since rotation is a linear transformation, we're just drawing out geometrically. And you can see that it's going to have this feature geometrically. That this is going to get mapped to that vector there, and that these are right angles. So we see that first feature of the linear transformation, how it behaves with vector addition. Now, if we consider scalar multiplication, let's say instead of u, we consider 2 times u. So that would be 2u. And then we take the vector 2u, and then we act upon it with r. So that'll generate r of 2u. This is the same thing as taking r of u, which was the vector from here to here, and then scaling by 2, which you can see that's true. That's going to be equal to 2 times r of u. It also behaves nicely with scalar multiplication. And that r acting upon the vector 2u is the same thing as r of u times 2. We can use our knowledge of geometric algebra to show that rotation is indeed a linear transformation. So if we have some arbitrary vector, let's say alpha x plus beta y, and we rotate that, we know that this is going to be given by something in the following form. Let cursive r be a rotor, and let cursive r dagger be the correspondent dagger rotor, and it acts upon that vector in the two-sided fashion that we're used to, that vector alpha x plus beta y. And if we can show that this thing here is equal to alpha times r of x plus beta r of y, then that suffices to show that r is a linear transformation. So let's manipulate the right-hand side here. We can distribute the r and r dagger to both terms here. So this is going to be equal to r times alpha x r dagger plus r beta y r dagger. Alpha and beta are just scalars, so I'm going to move the alpha out front and the beta out front. So this is equal to alpha r x r dagger plus beta r y r dagger. And what is rx r dagger? That's just normal r, where r represents the map itself, r of x, plus beta. What is ry r dagger? Well, it's just r of y. And that's what we sought to prove. So r, which is a rotation, is indeed a linear transformation. Let's consider another example of a linear transformation, namely projection, where I project vectors onto another vector. Let's say I have some vector onto which I'm going to project other vectors. Let me call that w. Let's say I have two other vectors. Let's say u, and I have v over here. Now what I'm going to do is I'm going to project u onto w in the following way. I'm going to trace a line segment down to w such that it's at right angles. And then this vector from here to here is going to be the projected vector onto w. You can see it's in the same direction as w. I'm going to call that p of u, where p is the projection function. Similar sort of thing for v, project it onto w, and that'll give me p of v. And then I'm going to consider the sum of p and v and p of u. That'll give me approximately this vector here. So that vector will be p of u plus p of v. Now, if projection is a linear operator, if it's a linear transformation, which it is, this vector from here to here, p of u plus p of v, should be the same as taking u plus v and then projecting it, which I'll attempt to draw in here. So that'll be just moving v from there to there, and then considering the vector sum, which will be u plus v. And then I take that vector and then I project. So if p is a linear transformation, which it is, the vector from here to here, which we saw before as p of u plus p of v, is also equal to p of u plus v. And again, let's use our knowledge of geometric algebra to prove that projection is indeed a linear operator, linear transformation. So let's again let p be the function which projects. Consider an arbitrary vector alpha x plus beta y. And let's suppose we're projecting it onto some other vector z. Now we know from our knowledge of geometric algebra that this is going to be given by something of the following form. The most general equation, if you remember, if we have u and we want to project onto another vector v, that's going to be given by u dot v, v inverse. So when we use this formula over here and we project it onto, let's say, z, this is going to go in place of u, and then we just change the v to a z. So we get alpha x plus beta y dotted with z. Then that scalar is going to be multiplied by z inverse. Now we can just utilize the features of the dot product to write alpha times x dot z plus beta times y dot z, still times z inverse. And then we just distribute the z inverse to both terms. So we have alpha times x dot z, z inverse, plus beta y dot z, z inverse. Now this thing is equal to the projection of x onto z, and this thing is equal to the projection of y onto z. So we see that this is equal to alpha times p of x plus beta times p of y. which suffices to show that P is a linear transformation, which is what we sought to show. And one other thing you can see, just returning to this diagram, is that projection behaves nicely with scalar multiplication. Let's consider, instead of V, we consider 2 times V, and then project. We get something approximately there. That right there is P of 2V. And we've proved that projection is linear transformation. So that's also equal to 2 times this vector. So that you just scale that by 2 as well. It's equal to 2 times P of V. Now let's think a little bit more about linear transformations and prove a number of very important facts about linear transformations. First, what I'm going to do is consider a scalar multiple of a linear transformation. That is, let's say I have some linear transformation called f, and I consider the linear transformation, which I'm going to call lambda f, where lambda is some scalar. And this transformation is, by definition, the way it works upon a vector x is going to be in the following way. Lambda of f, lambda times f, acting upon x as f of x times that same scalar lambda. So this is what this transformation is going to be doing. Now I claim that if f is a linear transformation, then lambda f, defined in the following way, is also a linear transformation. So a scalar multiple of a linear transformation is itself a linear transformation. That's what we're trying to show in this first proof here. It's not too difficult to show. Let's take lambda f and operate upon some arbitrary vector, alpha x plus beta y, where again, alpha and beta are scalars, x and y are vectors. We use the definition above. This acts upon that vector in the following way. We take f of alpha x plus beta y and multiply on the left by lambda. Now, by assumption, f is a linear transformation itself, so we can break it apart in the way that we've been used to. Alpha times f of x plus beta times f of y. Now we may distribute the lambda to both terms, in that we have lambda alpha times f of x plus lambda beta times f of y. We may swap the order there. So we have alpha lambda f of x plus beta lambda f of y. Now we just use this definition in reverse. What is this thing here? Well, that is simply lambda f operating upon x. And what is that thing there? That is going to be lambda f operating upon y. So we have this left-hand side is equal to the right-hand side, which completes that proof. That is, that if we have a linear transformation f, then a scalar multiple of that linear transformation is itself a linear transformation. Let's consider a situation which is slightly more interesting. Let's consider the sum of 2 linear transformations. That is, let's suppose I have f and g, which are both linear transformations themselves. Let's consider the summed linear transformation, f plus g altogether, which is defined in the following way, that f plus g operates upon x in the following way, such that it's equal to f of x plus g of x. Now I claim that if f and g are linear transformations, then the sum linear transformation, f plus g, defined in the following way, is also a linear transformation. To prove that, we just use the same technique as before. Consider the way f plus g operates upon an arbitrary vector, alpha x plus beta y. Now use the definition here of what it means to take the summed linear transformation. So we apply f to alpha x plus beta y plus g alpha x plus beta y. Now f and g are by assumption linear transformations, so we may break them both apart. So that first term is equal to alpha times f of x plus beta times f of y. The second term is equal to alpha times g of x plus beta times g of y. Now, we just have to rewrite this. What we're going to do is sum this first term with the third term here. And we write that as alpha times f of x plus g of x plus, and then we're going to sum the second and the fourth terms. So it's going to be beta times f of y plus g of y. And then once again, we use the definition in reverse. So what is this first? What is this factor here equal to? Well, that's going to be, just going in reverse, it's going to be f plus g acting upon x plus beta. And what is this second? What is this factor in the second term equal to? Well, that's just f plus g acting upon y, which is what we intended to show. That if f and g are linear transformations, then the sum linear transformation, called f plus g, defined in the following way, is also a linear transformation. So the sum of two linear transformations is itself a linear transformation. Now the third thing I'd like to prove, which is the more interesting one, I suppose, is that the composite of two linear transformations is itself a linear transformation. That is, if I have two linear transformations, let's say f and g, and I compose them, that is gx first, then f, then the composite linear transformation, which I call fg, is itself a linear transformation. So fg is going to operate upon x in the following way. So what it means to say fg, the composite transformation acting upon x, is to first consider g of x, let g operate upon x first, and then we operate with f. So that's what it means to have a composite transformation like that. So I claim that if f and g are themselves linear transformations, and that it follows that the composite transformation fg is itself a linear transformation. And we use the same technique once again. So we consider the operation of fg upon alpha x plus beta y. Use the definition here. So we first operate upon that with g. So g of alpha x plus beta y. And then we operate with f. So g is a linear transformation, so we may break that apart. So there's going to be f of alpha times g of x plus beta g of y. Now f is itself a linear transformation, so we may also break this apart. We may break the sum apart and move the scalars out front. So this first term is going to be alpha times f of g of x plus beta times f of g of y. And the last step is to use the definition in reverse. What is this factor equal to? And what is this factor equal to? So it's going to be alpha times fg, the composite transformation acting upon x, plus beta times the composite transformation acting upon y. So this is equal to this, which proves that the composite of two linear transformations is itself a linear transformation. Another interesting feature we can show about linear transformations is that they behave according to the associative rule, which is if I have three transformations, let's say f, g, and h, then we may say that f and gh together is the same as fg together times h. How do we show this? Well, let's look at the left-hand side first. Let's consider how it operates upon x. So we have f, gh taken together, operates upon x. What does this mean? This means that we have the composite transformation gh operating on x first. So gh operates upon x, which then gets operated upon by f. But we see that, what is this? The composite gh operating upon x. That's equal to H first, then G. So that's what we get when we expand that. Now let's look at the right-hand side. So we have FG, H first, and then the composite FG. This is going to operate upon X. So we see that H operates upon X first. So we have H of X, which is then operated upon by the composite FG. What does this composite FG mean? Well, it means take this, operate upon it by G first. So we have G of H of X, and then by F. And we see that these two are equal, which proves this statement here. So linear transformations obey the associative rule. Now, it should go without saying that they are not commutative. There are many examples of linear transformations we've already considered in this series, which are not commutative. Rotations are an easy example of where linear transformations are not commutative. So it is not true in general to say that FG is equal to GF. That's not true in general. It's true in some cases, but not true in general. We may also prove the distributive rule for linear transformations. That is, if I have three linear transformations, F, G, and H, and we consider F of G plus H, this is equal to FG plus FH. How do we show this? Let's look at the left-hand side and consider how it operates upon some vector X. Now we have a composite between two transformations here. So we have G plus H together, which acts upon X first and then F. So let's write that. So we have G plus H, X upon X, and then F X upon that. And then we have the sum between two linear transformations, and we know how that acts upon X. So we have F of G of X plus H of X. And then F is a linear transformation, so we may break it apart over addition. So this is equal to F of G of X plus F of H of X. Now, what is this first thing? This is FG acting upon X plus, and once again, we have a composite, so this is FH acting upon X. And that suffices to show this statement. This statement is just a statement about the linear transformations themselves, just with the X removed out and not considered or suppressed. Now, this is a series on geometric algebra, so we'd like to include some geometric algebra concepts here. So let's suppose we have some linear transformation F, which is fully defined, and we know how it acts upon the vectors, the grade 1 objects. But in our geometric algebra, we have things other than grade 1 elements, of course. We have things like bivectors and trivectors. So how do we extend this linear transformation F, which is defined upon the vectors, to also be defined upon other objects like bivectors and trivectors and beyond, for example? Well, this linear transformation, which is induced by the defined linear transformation on the vectors, is induced or generated in a very natural way. So let's say we have F and we want to act upon a bivector. Let's say U wedge V. How should F act upon U wedge V? And in such a way that it preserves the structure of the outer product. Well, the way to have F act upon this is to define it based upon what we know about the vectors. So this is going to be equal to F of U wedge F of V. Very simple. So the way F acts upon the wedge U wedge V is the wedging of how F acts upon U with how F acts upon V. Very simple, but let's try to draw a picture just to see what's going on here. So let's suppose we have some pair of vectors here. Let's say we have U and V. And we consider the bivector U wedge V. Let's suppose we want the induced linear transformation F to act upon this bivector u wedge v. So it's going to map it to another bivector. Just as f was mapping vectors to vectors before, now we're going to extend f to allow it to map bivectors to bivectors. So what bivector will this get mapped to? Well, that's easy to say. Let's suppose u gets mapped through f to this vector here. It's going to be f of u. And let's suppose v gets mapped to that vector, f of v. Then f of u wedge v is going to be the wedging between those two vectors. It's going to be the wedge between this and this. So let me try to draw that in there. So it's going to be that wedge product. It's going to be f of u wedge f of v. So f is going to map this bivector here to that bivector. So this bivector here is f of u wedge v. So you can see we can extend what f is mapping to the bivectors in this very simple way. And if you have something in the argument which doesn't look like that, perhaps it's a sum of blades, let's say f of a wedge b plus c wedge d. Well, you just let f act upon this in the natural way to have linearity, which is that this is going to act in such a way as have f of a wedge b plus f of c wedge d. And these two terms are defined above. Scalar multiplication is going to work in the way you'd expect as well. So this induced linear transformation that operates now upon the bivectors, which is generated from the linear transformation which acts upon the vectors, the grade 1s, is called an automorphism because it preserves the structure of the outer product. So we've extended f from its initial acting upon vectors, or grade 1s only. We've extended it to the bivectors, the grade 2s. Now let's extend it one grade further to the grade 3s, the trivectors. So let's consider f, the induced linear transformation, now acting upon a trivector. Let's say u wedge v wedge w. And what is the induced linear transformation upon the trivectors here? How should f act upon this to preserve the structure of the wedge product or the outer product? Well, that's easy to see. Just use analogous reasoning here. That's going to be f of u wedge f of v wedge f of w. So the resultant trivector here is going to be the wedging between these three vectors here, which come from the original linear transformation acting upon the grade 1s, the vectors. The only other thing to consider here, I suppose, is how a scalar multiple of a trivector would be outputted. That is, if we have f of lambda all times u wedge v wedge w, which should go on the right-hand side. But as in the above case, this is built right into the original definition, just flows right out as a consequence of this. And what we know about trivectors, because this stuff inside the argument is also equal to lambda of u, if you just bring this scalar right into the first vector in the wedge product there. Lambda u wedge v wedge w. Now you just apply this first definition here, and you just split it apart over the outer products, the wedge products. So this is going to be f acting upon lambda u wedge f of v wedge f of w. F is a linear transformation. It's already been defined over the vectors, so this scale lambda can be yanked out. It can either be regarded as acting upon the first vector here in the wedge product, wedge f of v wedge f of w, or you can just yank it all the way out front. We have lambda times the entire thing, f of u wedge f of v f of w. And the analogous reasoning would apply here with regard to scalars. Now you can understand what's going on here when f acts upon these trivectors in an analogous way to what we've try to draw over here. I won't draw because it's a little bit more difficult to draw and the diagram tends to get a little cluttered. But what we have is that a wedging between three vectors, u, v, and w, so u, wedge v, wedge w. The result of this is some blob of volume, which is going to have some intrinsic orientation, either plus or minus, according to the right-hand rule. Now, F is going to operate upon that to generate some other oriented blob of volume. And the blob of volume that you get is obtained by considering how Fx upon u, wedging that with how Fx upon v, then wedging that with how Fx upon w. Now, the induced linear transformation for how Fx upon trivectors is actually very interesting in the setting of linear algebra, for the reason that when Fx upon any trivector, again, let's say x, wedge y, wedge z, just changing up the letters a little, whatever shows up on the right-hand side has got to be a trivector, but because these blobs of volume only have orientation, they don't really have a direction in the same sense that the bivector has a direction, like the bivector could rotate and such. So whatever shows up on the right-hand side is going to be some scalar multiple of the input argument. So whatever shows up on the right-hand side is going to be some scalar multiple. I'll call it lambda for now. It's going to be lambda times x, wedge y, wedge z. Now, if you just consider what lambda is, just divide both sides by x, wedge y, wedge z. So we have f of x, wedge y, wedge z. Divide by x, wedge y, wedge z. What is lambda doing here? It's a scalar, and it's a ratio between the blob of volume that comes out as a result of f compared to the original blob of volume. So it gives the scaling factor upon the volume. For instance, if lambda were 2, what that means is that the blob of volume that comes out is twice the volume of the original blob. So the volume gets expanded by a factor of 2. Now, lambda can, of course, be positive or negative, because volumes have an orientation such that we can consider negative volumes. So if lambda is, let's say, -1, what that means is the magnitude of the volume is unchanged by the linear transformation, but its orientation is flipped. That's what the minus sign means. And if it were -2, that would mean that the orientation is both reversed, it's flipped, and it's expanded by a factor of 2. So this lambda value, which is simply the ratio between f of x, wedge y, wedge z with x, wedge y, wedge z, is a very important quantity for the linear transformation. And this scalar is traditionally called the determinant of the linear transformation f. So we may write that f of x, wedge y, wedge z is equal to some scalar, which we're now calling the determinant, or det f, times x, wedge y, wedge z. And we've already given the interpretation for the determinant. It's the scaling factor upon the volume, also taking into account the orientation. So the determinant can be positive or negative, and the absolute value of that gives the scaling factor. If it's -2, then, as I said, the orientation is reversed, and the volume, just the magnitude, is expanded by a factor of 2. Now, from this line, we may also write the following. If x, wedge y, wedge z were such that it's equal to the unit pseudoscalar, the unit blob of volume, which has the positive orientation, which we've been calling in the series big I, which in our orthonormal basis was just E1, E2, E3. We may write that this is equal to det f times I. And we may also write that the determinant of f, just that scalar, the grade 0, is equal to f of I times I inverse, which we obtain just by multiplying both sides by I inverse. And I times I inverse is, of course, 1. So this we take as the definition of the determinant of a linear transformation. It's given by considering how the induced linear transformation acts upon the unit pseudoscalar and then times I inverse. And the action of I inverse is just to get rid of the E1, E2, E3, just to consider the scalar only, what's sitting out front. Now you'll notice that when we've been talking about the determinant here, one mathematical object has been missing from the discussion, and that's a matrix. We haven't had any need to talk about matrices at all, and we don't need them to define what a determinant is. Now usually when linear algebra is taught, it's taught in terms that the determinant is thought of as a special number which is associated with a matrix, which is true to say, but the problem is what the determinant represents as something which is intrinsic to the linear transformation itself is very much masked by what goes on when thinking of the determinant as a number associated with a matrix, and that you really have to work to that insight that the determinant has something to do with the scaling factor upon, if you're working in 3 dimensions, upon the volume, or if you're working in 2 dimensions, upon the areas. Like, you really have to work to that insight, whereas at the approach that we've adopted here, it's built right in. The interpretation just flows from what the definition is. It's obvious what the determinant of f is. Now, another piece of evidence for how natural this approach is compared to the matrix approach to determinants is that we can prove a very important statement about linear transformations and their determinants very, very easily. Namely that if we have a composite of two linear transformations, to find the determinant of that, that's simply the product of the determinants of the individual linear transformations. That is, if we consider the determinant of fg, where f and g are just two linear transformations, the determinant of this is simply the product of determinants of the transformations themselves. So det f times det g. Now, as I claim, the proof of this is extremely simple. What is the left-hand side, by definition? The determinant of fg is how this composite linear transformation acts upon the pseudoscalar I times I inverse. Now, what is fg, the composite applied to I? Well, this is going to be f of g of I times I inverse. What is g of I? Well, that's going to get mapped to something times I, and that special something is called the determinant of g in this case. So g of I is equal to det g times I inverse. Now what we can do is that since f is a linear transformation, we can remove the det g and place it out front. So det g times f of I times I inverse. And what is this thing here? That's just det f. So that's det g times det f. And these are scalars, so we can just commute as we please. So that's equal to det f times det g. And the left-hand side was det fg. And that's it. The proof of this using matrices is extremely complicated. It's extremely tedious. And oftentimes, if you're learning linear algebra in the typical place where you learn it in the university curriculum, you don't even understand why this is true. And of course, the interpretation of all this is extremely natural. So let's suppose you had two linear transformations. Let's say you had g. It's a linear transformation such that it expands the volume of I by a factor of 2. So its determinant would be 2. But then let's say f was, let's say, a reflection, which is a linear transformation, which is going to flip the orientation of that volume. So it's going to switch it to a minus. So the product there is minus 2. And that's the determinant of the combined operation when you consider those two linear transformations together in that composite way. Now, another consequence of this fact is that the determinant of an inverse linear transformation is simply the reciprocal of the determinant of the original linear transformation. And to see why that is, we can simply substitute G is equal to F inverse, where F inverse is the inverse linear transformation. On the left-hand side, we have det of F inverse. On the right-hand side, we have det F times det F inverse. Now, F times F inverse is simply the identity operator, which doesn't do anything to anything, just keeps it the same, which I'm going to notate as 1 hat, where this means the identity operator. That's again equal to det F times det F inverse. Therefore, det F inverse is equal to the determinant of the identity operator over det F. Now, what is the determinant of the identity operator? Well, let's not think in terms of matrices. Let's think in terms of operations upon the pseudoscalar. So let's examine how the identity operator acts upon the pseudoscalar I. Well, it's the identity, so this is just equal to I. What's the scalar sitting up front? Well, it's 1. So this is equal to 1. So we have det F inverse is equal to 1 over det F. Very simple. Let's consider a couple other examples of where we consider the determinant of a linear transformation without recourse to matrices or anything like that. Let's consider the example where the linear transformation is a rotation. So let's again designate the rotation, that linear transformation, as R. So let's ask, what is the determinant of R? Now, of course, this is going to be equal to how R acts upon the pseudoscalar I times I inverse. Now, just use your intuition, your mathematical reasoning a little bit. Think about a blob of volume, which is getting rotated by some amount through some angle and through some bivector. Now, does the rotation of a blob of volume change the amount of volume contained within the blob? Well, no. So the determinant must be either plus or minus 1. Does it change the orientation? Can it change a positive volume to a minus volume or a minus to a positive? Well, no. Therefore, we expect that the determinant of a rotation is simply 1. Now let's use our analogy of geometric algebra with rotors to find out what this thing is. So this is going to be just using our notation that we've used before. So let cursive R be the rotor in question. So this is going to be R dagger times I inverse. Now the pseudoscalar commutes with everything else. Therefore, I can commute these two. So I'm going to write R dagger times I inverse. R dagger is equal to 1. And I inverse is also equal to 1. So yes, this is equal to 1. So det R is equal to 1. Put another way, R acts upon I to preserve it. Ri is equal to I, and the coefficient sitting out front is, of course, 1. So the determinant of R is equal to 1. So rotations have a determinant of 1. So we know that without any sort of matrix operation. We just know that through geometric algebra. Let's consider another example of a linear transformation, ask what its determinant is. We talked about projection before, where we project everything onto a vector. Let's work in 3 dimensions and ask what the determinant of that linear transformation P is. So let's say we have some special vector, and we want to project everything onto that vector. So the induced transformation P, it's going to act on the pseudoscalar I. So also equal to P of E1, wedge E2, wedge E3, which is going to be the determinant of P times I, some scalar multiple of I. Now, we know that this is going to be equal to P of E1, wedge P of E2, wedge P of E3. But since every vector is getting projected onto this special vector U, if we just consider this vector and this vector, whatever happens here, this vector is going to be some scalar multiple of that vector there. And when you wedge two vectors that are scalar multiples of one another, then that wedges 0. So this whole thing wedges to 0. What's the coefficient sitting out front? Well, this is the same thing as 0 times I. Therefore, the determinant of the projection transformation is 0. And of course, what's the geometric interpretation of this in terms of blobs of volume? Well, the entire blob of volume gets collapsed down onto the line here, onto this vector. It gets squished down and it has 0 volume. That's the interpretation. And by using similar reasoning, you can prove that if we have some projection transformation, which we'll call P prime, and this transformation is, instead of projecting everything onto a special vector, you project everything onto a plane. In this case, what is the determinant of P prime going to be? Well, just by geometric reasoning, if everything's getting projected onto the plane, that blob of volume, the unit pseudoscalar, that's going to get squished down onto the plane, in which case it has 0 volume. So the determinant of P prime must be 0. And as an exercise, you can prove this in a more rigorous way. But the point is, just the geometric intuition alone is going to tell you what the determinant of this linear transformation is going to be, at least for easy ones like this. Now, this may be obvious already, but you have to slightly adjust your interpretation of the determinant depending upon the number of dimensions in which you're working. Although it's not all that different, because there's a unifying concept of n-dimensional volume that ties everything together. For instance, if we're working in 3 dimensions, as we have been supposing in some of these examples, the determinant is going to be thought in relation to the stretching or contraction of the volume, and also potentially flipping its orientation. If we move back to 2 dimensions, it's going to be thought in relation to how areas stretch or contract, also flipping orientation potentially. Going down to 1 dimension, because the pseudoscalar there is going to be of grade 1, we think in terms of how it stretches or contracts lengths. If we go higher than 3 dimensions, then you just think of the n-dimensional extension of the volume concept that we're using in 3 dimensions. So it's going to be a stretching or contracting of the n-dimensional volume, also potentially flipping its orientation. But as you can see, there's an underlying concept that unifies all of them. You consider the highest graded element of the geometric algebra built upon that vector space, and you consider how that expands or contracts, and also the change in orientation, if there is one. That's how you interpret the determinant of a linear transformation in a totally unified way. So that'll do it for this video. Hopefully you've seen how much we know about linear transformations even before we start talking about matrices, and seen how this approach generates results in a much more natural way. And in my opinion, this approach is superior because linear algebra is primarily the study of the linear transformation, and only secondarily the study of matrices, for the reason that matrices represent linear transformations and they really only make sense in light of linear transformations. So we have to, when we're studying linear algebra, we have to keep our eye upon the linear transformation itself and only secondarily upon matrices as a sort of computational tool. But we'll get into that in the next video. We'll see how all this stuff ties into matrices and is really the basis for how one works with matrices in a reasonable way in linear algebra, and how this ties into the linear transformation. So hopefully I see you in the next video. Thanks again for watching.